Very well. So our next speaker is Chien-Yu Chou.
Yeah.
Sorry. And he's going to tell us about probability transport approach to flow-based sampling in field theory. Thank you.
Yeah. Okay. Thank you for the introduction. And my name is Chien-Yu Chou. I'm also graduated in NTU, and I'm now in RIKEN-iTHEMS. And I would like to thank the organizer to invite me for this short talk. And so this work is about the probability transport approach to this flow-based sampling. And this work is in collaboration with Professor Nishimura in KK and Professor Chichiya in Shizuoka University and their students. And one of them is Wang Zhenzong. He's also graduated from NTU. I think some of you know him pretty well. So the background of this work is that we attended a lattice workshop in Tokyo University, and we're fascinated about some recent work on generating model and neural network in lattice field theory, and also some physics informed kernels. So before jumping into this big black box of training neural network, and we would like to fill up some of the gaps we think pretty important, or we need some physics significance in this computational science. So one of it is the cost and gain of this physics information we put into this training or fitting. So here what we use is this optimal probability transport. So it's like just how we so we have a pile of sand, how we put it into another shape or move it to another place, and what is the optimal way to do that. And the second criteria is how, and during this process, how we maintain a controlled statistical error. And finally, of course, the most important is the correctness of the result. So, and also its ultimate application to lattice gauge, the full lattice QCD simulation, etc. So this is what we would like to focus in this work. So this is an ongoing work, so it's not published yet. So let us start from some motivation of this flow-based sampling. So I'm also not an expert in lattice field theory, so I will talk about it briefly. So the standard or traditional way to lattice calculation is Markov chain Monte Carlo, but even if you did it correctly, you have detail balance and invertibility, and it will become ergodic eventually, but it can still explore the target distribution pretty slowly. And here are two examples. For example, on the right-hand side, you can see it from maybe every Monte Carlo textbook. So it's just many of the important regions are separated by action barriers. So and in lattice field theory, it will appear like a topological freezing, and each topological sectors are like separated. So for a continuous trajectory, it will go across the barrier very rarely, and even if you have go through each of the potential vacua, it's still very hard to get the correct relative weight between each of the potential vacua. So it is is one of the example, and the other one on the left hand side, it is the critical slowing down. So even if you only have one continuous distribution, some of the collective directions might be very slow, or the correlation length is very long. So if you have some successive samples in some collective version, it might appear more slowly. So it will make the autocorrection length of the HMC much longer in such situation. So yeah, it happens as a critical slowing down in the simulation. So and more specifically, so for example, so here is a more detailed explanation of critical slowing down. So in the continuous critical point, it is a point where the correction length will diverge or goes to infinity. So, but in finite lattice, the correlative, you can find a critical sequence by fixing the disk C is the correction length, and when your lattice grows, you fix the correction length and the lattice size to be a constant, and then so when you take the L to the infinity to the large lattice size, you will find that the correction length become longer and longer. So it will be you will take longer and longer to get a independent sample in HMC. So in this published work, they fitted the result to according to the lattice size. So the estimate of the scaling of the independent point is like L to the fourth. So yeah, so it's like to the v squared. So it is pretty large for them. So I think their ultimate goal is get like order v or order L squared for some optimal algorithm to overcome this critical slowing down. So yeah, and here are another example. So we take the 2DU1 gauge theory as an example. So the action is written like this: is sum of the pocket. The theta p is the pocket angle. So and since we defined it on a periodic lattice, so the Q, the topological charge is if you sum over the argument of the pocket angles, it will be a multiple of 2 pi. So this Q will define the topological number, and the distribution will be distributed in the integer sectors of this Q. So if you want to jump from 1, for example, Q equals to 0 to 1, then at least one of the pocket angles should cross theta equals to 0 or theta equals to pi. So there will be a barrier of S approximately like 2 beta between each of the sector. And yeah, so and in this work they also fit the autocorrection length of this HMC, traditional HMC, to beta. So it is much worse. So it's much worse. So it is like exponential in beta. So it will also cause a serious problem. Okay, so this is the motivation of flow-based sampler. So you can see that even you have correct proposal locally with HMC or Markov chain, you still missed some important global structure of the target distribution. So yeah, so there are two prominent roles of flow-based sampling to give a more global proposal of the sampler. So one of it is the normalizing flow. So it's basically two steps. First, they will train a neural network to map a simpler distribution, like maybe Gaussian, to the target distribution, maybe double peak, and then followed by a correction like Metropolis Hastings. So and the acceptance rate of that Metropolis steps will tell them how good is the neural network trained. And the other one, the other interesting one is the diffusion model. So they will add noise into their trained data. So it will eventually become a complete noise, and then they will learn the inverse the inverse process so that they become a generator of the target ensemble. So yeah, and this work we are more closely to the left case, but we're not using neural network. We're using an action-derived optimal transport as a proposal, and for the correction part, we're using this sequential Monte Carlo, and I will explain what are they later. So yeah, so the method itself. So first of all, we have a prescribed path of action. Then it will determine in the beginning that how we design the probability to change from this rho 0 is simpler. For example, Gaussian. Then we can generate a lot of points with respect to this Gaussian in the beginning, and then trying to flow it to the target distribution along this prescribed path. So after this prescribed path and the action is determined, then this k of t here describes the velocity of each point in this ensemble. Then it should comply to this continuity equation. So this is the starting point. But so we have this continuity equation, but it does not determine this velocity uniquely. It is underdetermined partial differential equation. So it is straightforward because naturally we will think that this 1p to double p, the right hand side goes to right, the left hand side goes to left, but it can also swap. Then it will still give the same final double p structure. So, and this is where we let the optimal transport comes in. So we need a selection rule to this underdetermined equation. So we adopted the optimal transport the idea. So here we would like to minimize this integral. So it's just like rho times v squared. So the integral over rho times v squared. So it's just we want the flow has the minimum kinetic energy. So if you plug it, if you put it, use the continuity equation as Lagrange multiplier and do variation and integration by parts, you will find that the selected optimal transport for this velocity will be a gradient form of some psi t. So you plug it back, and then we will the continuity equation in the end will be something like Poisson equation. So the practically in our calculation, we will simply approximate this phi of t with some symmetry compatible finite lower order basis, and yeah, so it will become very cheap. For example, we only need 2 or 4 coefficients in this side of t, and it will already capture most of the physics information in this Poisson equation. So yes.
Capital S of
capital S of t is this define this change of action. So yeah. So it defines rho as well. Yeah. So this path is already determined in the beginning. Yeah, and then along this path we would like to find the optimal transport. Okay, so but as we have said, we only use some lower order symmetry compatible finite basis. So this is only approximate. So we also need some exactness procedure to get a correct result. So after we apply the move, so it will be some mapping like T with this optimal transport. Then we will you will put it back to this delta L to do reweighting, and then after reweighting, since the T this distribution of y will still have some discrepancy with the target distribution. So such discrepancy will result in that some of the points in the sum will become more important than the other. So the the weight becomes uneven. Then at some point, if some of the weights become too large, we will do a rectangle. So you should duplicate the important ones and then drop off the unimportant ones, and then finally the rejuvenate. So this rejuvenate is target invariant update. For example, you can just do some very few steps of HMC to just perturb this ensemble at each step. So this is the sequential Monte Carlo framework, and it can adopt any kind of mapping. So, but in this work we adopt the optimal transport mapping. So, yeah. So here is our first. So we apply it to two different models. The first is the 2D 5-4 scalar field. So in this model, we have quadratic term and a quadratic term and a quadratic term. And by tuning a parameter, it can be in three different phases. The first is we will start from Gaussian and then push it to these symmetric phases and these near critical phases and the broken phases. So this is just schematics, and here we show exactly in the simulation how the distribution evolves along the flow time from the left end is the Gaussian and the right end is the target distribution. So yeah, so and then this is the endpoint distribution of the magnetization, and there are the dashed line are the reference. So the reference is calculated some specified algorithm for 2D 5-4. So there are some specified algorithm for 2D 5-4 to get a very accurate result. So the magnetization distribution and the endpoint observable is very close to each other. So this so this shows that this OTSMC gives some pretty good result, and the cost is not very high. And the other one is the 2D U1 theory. So this is also described as the example of topological freezing. So this graph is the distribution of the topological chart. So when we start from beta, so the flow, so here the S of t will start from beta equal to 0 and all the way to beta equal to 8. And we will expect that if it's successful, then the distribution of this topological charge will change smoothly and without any problem. So yeah, so here is the result of actual simulation. So from smaller beta, from beta equals 0, since we only have power measure, so it's pretty flat in the topological charge distribution, and in the end it will centralize to a much narrower distribution. So yeah, we can compare it since 2D1 is solvable. So we can compare it to analytic results. So yeah, here we have the distribution, and on the right hand side we have average of suspected and the susceptibility, and yeah, both of them. And even if with this such global observable, it still gives correct results. So yeah, so this is what we have found in these two specific models. So yeah, so and yeah, so for 2D54 we tested in 3 distinct phase geometries, and all of them give correct result. And also we test endpoint with both local and global observables. For 2D-U1, also we already go to the weak coupling parameter setting, and the evolution in the distribution of the topological charge is still correct. So yeah, it gives us some. So although it is still some fixed lattice, and also yeah, we choose the lattice is like order 10 and 20, and yeah, we haven't showed the scaling, but it already is a very good proof of concept that it can give correct result with this framework. So yeah, here is the conclusion and the outlook. So yeah, what we would like to do next is, so here we only work on fixed lattice size and trying to push it from a simple distribution to the target distribution. But this framework can be applied to more complicated and more suitable for large lattice simulation. So we can start from a smaller lattice size and get a target example like L by L, for example 3 by 3 or 2 by 2, and then we can push it to 2L by 2L by adding another 3L squared Gaussian noise, and then you can do the inverse Carter transform, and then the correct distribution on the smaller lattice can become the coarse distribution of the larger lattice, and then the optimal transport also can be used to push forward to correct the detail of the larger lattice. So this framework also applies really well to here, and also this we can still add neural network after this optimal transport proposal to maybe learn the residual or learn some longer motion, etc. So this is pretty a lot of good prospect, and yeah, and the next goal is to check the critical scalar sequence and also the weak coupling sequence to check if the scaling is also good in these two problems. Yeah, so I think that's it for my talk. Thank you very much.
Thank you very much for the nice presentation. Questions?
So thank you for the nice talk. So can you explain again the technique that you used in the optimal transport when you minimize K star?
Oh, okay. So, you mean?
Yeah, because based on the flow equation, I think rho depends on K.
Rho depends on
KT.
This rho depends only on S. Then then this K will depend. Yeah, this K also after rho is determined, this K should satisfy this equation.
Oh, that is the equation.
So K is not uniquely determined.
I see. I see.
Yeah. So many velocity of each point in the ensemble can give the same final shape. So in this sense, we need a selection rule. So the selection rule we choose is this optimal transport. Yeah. So we want this K to further satisfy that you minimize the connecting energy. Yeah. Yeah, and equivalently, if you combine these two, this means that this velocity should be a form of gradient of something. Yeah. Any other term outside of this gradient will increase the kinetic energy. Yeah.
Thank you for your talk. So still on this slide, actually, I'm a bit surprised that psi you just need to solve this linear elliptic problem.
Yeah.
I would expect it to be more non-linear, like a Monge-Ampère operator instead of an elliptic operator. No?
Yeah, I think it's like what I said in the beginning. It's like a cost and gain in this physics information. So here it is only linear, and we use very few bases. And I can mention here that this. So this delta L is important here since it not only guarantees the correctness by relating. You can also measure how good this T is. So we can estimate how good if we only use this linear equation and finite basis, and we can.
I'm sorry. It's just where does it come from? Because I feel this K star, so psi, is the solution of your optimization problem, right?
That's. I mean, how?
So this equation, this linear elliptic equation on psi, where does it come from?
Oh, you mean this?
Yes.
So, so this. So first of all, if you want to minimize this, so we have this equation, and then you can add another. At this term times the psi as a multiplier, and then do direction, and then you will get K should be gradient of that the psi, and then you just plug it back to this continuity equation, and also plug this rho as this, and then you will get this equation.
Okay.
Yeah.
Thank you.
Yeah, so I also see very strong resemblance with the physics-informed kernels, so the generalized flow equation, because you choose here a target action that you also track this field, let's say this redefinition, right? So you kind of separate the information into different equations. But I wonder whether you plan to apply this to sign problems or.
Sign problem. For sign problem, then we don't have such good. The continuity equation will be different, and also, I think for now it does not apply to sign problem very directly. Yeah, we are also think about that, but okay. It's not very straightforward.
All right, more questions? If not, let's thank Chien-Yu.
Thank you.